and thank you for having me here. So today's topic, we're going to teach you how to survive in this cold weather. Just kidding here. So today's topic, we'll be talking about how to enhance survival analysis by improving calibration without compromising discrimination. So survival analysis predicts time until event. Here, the event can be either death, relapse, or service subscription. Let's assume we have a study period, 5-year study period, and we observe someone enrolled study, and then we observe some event happening on him. And then right now, everything is pretty standard and pretty similar to the regular regression tasks. However, survival analysis is unique due to the existence of censorship. So in here, we're specifically focusing on right censorship, where we do not know the true event times, but we know lower bound for the event times. So for the third patients, we have a file missing time. That means this is a time we lost track on the patient, and whatever happened afterwards, we do not know the information. And similar for the fourth patient, he's moving out of country, so we cannot keep track on him anymore. And for the last patients, he's still alive at the end of the study. However, because the study already ended, and we don't have any resources to track him down anymore as well. So he's censored at the study ending time. So right censoring is not as informative as uncensored subjects. However, they're not completely meaningless, making how to incorporate those censored subjects in the analysis an interesting topic. So we need to make some assumption here. So the first assumption is everyone will have an event time and a censor time. However, in the real world, we only observe the earlier happening time. So to illustrate the idea that maybe the first one, if he didn't die during the study, and if we can keep observing him, he might get moving out of country, and we lost track on him. And for the third subject, if we haven't had him file missing, he might be dead after some points. And another assumption we make is we assume conditional independent. That means the censoring time and event time are conditionally independent given the features. So previously, we're talking the study in the calendar time. However, to express this into the tabular data or like the data that machine can understand, we need to convert this into a study time. That everyone should have an time origin of 0. So we need to shift it everyone so that they have the same starting time. And then we can extract each subject using some feature like age, sex, and BMI. And then we have 2 labels for sensors for survival analysis dataset. The first label is called time, which is the observed time for every subject. It could be either event or sensor. And the second label is called event indicator, which is a binary indicator, indicates whether the time we observe is an event, which has an indicator value of 1. And if the observed time is a sensor time, then the event indicator is 0. Survival analysis try to estimate the individual survival distribution, or someone call it conditional survival distribution. It describes the survival probability for all future times given someone's feature. So in this figure, in this example, we can have the survival probability equals to 70% at 1 year for patient I. And similarly, we can extract some useful information from this distribution. For example, the predicted event time. And in this example, we're using median survival time or predicted median survival time. The predicted median survival time is defined as the time where the survival curve intersect with the 50% percentile line. So to formally express it will be shown in this. It is shown in this blue diamond here. And mathematically speaking, the formal definition of the median time is this. So we just covered some basic survival analysis background. Now we're going to introduce 2 important properties for survival analysis. One is called discrimination and one is called calibration. They are 2 important but distinct properties in survival analysis. So the first one is called discrimination, and someone call it a concordance index. So given the survival curve or individual survival distribution, a model can predict it. And so we have 4 patients, patient A to D, and we have a model that predicts the individual survival distribution for these 4 patients. And we also have the true label for them indicated by these stars. So the first thing we need to do is we need to extract the median survival time from this curve. And now let's get rid of everything else and just focusing on the predicted time and the observed time. So the discrimination calculates the proportion of all comparable pairs whose predicted order and observed or outcome orders are concordant. So the equation is kind of scary here, but we'll go through an example here. So for the first two subjects, the first pair, we can see that the predicted order is yellow ahead of blue, yellow ahead of green, and the observed time is green ahead of yellow. So that means the model incorrectly predicted for this pair. And for the second pair, we see that the predicted time and the predicted order and the true order are aligned. Both have yellow ahead of orange. And this one is the correctly predicted order. And for the third pair, the order are also correct. And we can keep doing this for every possible pairs in the data set. So one may notice that in the terminology, we define the discrimination as the proportion of all comparable pairs. What does it mean? So this is because for survival analysis, we have censorship, and we do not always know the true event time for every subject. So that means not every pair in the data set is a comparable pairs. So we make, for example, here. The first example, we have 2 uncensored subjects, or 2 subjects of who we know experience the events. So in this case, because the order of their event time are already known and deterministic, and of course, they're comparable pairs. And in the second case, where we have the first being the event patients or event subjects, and the second being the censored subjects, because for the second subject, the event time could happen anytime after his censored time, and concurrently, it is after the first subject's event time. So in this case, the order of their event time is also deterministic. So in this case, it's comparable pairs. And in the case 3, we have the earlier subjects being the censor, because the true event time for the earlier subjects can lie between anywhere, lie before the true event time for the second pair of second subjects, or the true event time after the second pairs. So in this case, the order is not deterministic and not comparable. And for the last case, we have 2 censored subjects, and of course, we do not know anything about their event time, so they're not comparable anymore. So one may wondering why discrimination is useful. We here make an example in the real world application. We have 5 cirrhosis patients. Cirrhosis patient means they have a bad liver, that they're suffering. And we have some limited clinical resources. In this case, of course, it's a liver. And we need to decide which patient among these 5 we will deliver this liver to. And let's say if a model can have a very good discrimination, then it can correctly order these cirrhosis patients according to their severity levels. So in this case, the first one in the wait list should be the highest one, the most severe patients among all. And after we define this wait list, we can determine that this liver should go to the top risk patients in the wait list. And what does calibration mean? So calibration has a very proper definition, and we here use an example of weatherman forecasting as an example. So assume a weatherman make a forecast between December 23rd to December 27th, and coincidentally, the forecast is all the same, 80% of snow for every day. So in one universe, let's say the universe we're living in, we observed the outcome after December 27th. And we already know that 4 of the days we experience the snow and 1 we do not. And in this case, exactly 80% of the days have snowing and 20 of the days not. So in this case, we can say that the prediction is pretty calibrated. That means the observed outcome and the predicted probability are aligned. in two other universe, let's say. The second universe, we have 5 snowing days. That means we observe 100% snowing. This is a little bit misaligned with what we predict. And in the third universe, we have 2 snowing days. This is, again, a little bit misaligned with what we predict. However, because of the sample size, we might still say that the weatherman is kind of accurate. It might be some randomness involved here. So we're not, we can still maybe believe this weatherman in the future. And then in the last case, we have, in the last universe, we did not observe any snow. And in this case, we can more confidently say that maybe the weatherman is not accurate and we should not listen to his weather forecasting anymore. So in this application or in this study, we're focusing on calibration for a distribution. So what does calibration for distribution means? So let's say we have a probability density function. It's a weird shape like this. It's drawn from a Weibull distribution. And we can randomly draw a sample from this distribution, illustrated by this orange dots here. And correspondingly, we can plot the cumulative density function and the survival function. Don't be overwhelmed by the equation, but it's just a simple integral of the probability density function. And we can calculate the correct corresponding position for this sample. Corresponding position for this sample on the cumulative density function and the survival function. And we can keep sampling. We can keep sampling 4 more. And each sample will have the same color here. And we can even sample more. In here, we sample 40 sample. We randomly sampled 40 instances. And the nice property from a probability distribution is that based on the inverse transform theory, the vertical location of the circles at the survival function is uniformly distributed between 0 and 1. So in this case, we have divided the probability interval between 0 and 1 into 4 subintervals. We have 0 to 25, 25 to 50%, 50 to 75%, and 75 to 100%. So because it should be uniformly distributed, so we can assume around 10 samples, because we in total draw 40 samples. So we should have around 10 samples in each interval. And we compare what we observe. We observe 12, 9, 10, 9 in these 4 intervals. And we can perform a chi-square test to test whether this observation and the prediction are aligned. And we can get a p-value. If the p-value is greater than 0.05, we say that the distribution are calibrated. And this comes to the formal definition of distribution calibration. So because in the real world application, each distribution we only observe 1 times. And previously, for each distribution, we draw 40 times. We draw a sample 40 times. So in this case, we only have 1 observations. And what we can do is find the survival probability at the event time and hope this survival probability at event time is uniformly distributed between 0 and 1. So for the blue sample, the patient A, it is located between 75 to 100%. And for the orange, it's between 25 to 50, and we can keep going on. You see that this histogram, like horizontal histogram, in the third figure, they are not very uniformly distributed. It's like you have 2 counts in the second interval, and you have 0 counts in the third interval. So formally speaking, or mathematically, to express this, we hope that the number of stars in each subinterval should have the exact proportion of the size of the interval. And then we can also perform a chi-square test and get a p-value to decide whether this distribution is calibrated or not. So how about censored subjects? Until now, we haven't touched about censored at all. So let's assume previously the example is the 4 patients are all uncensored. What if now patient A is a censored? We can, the patient A is expressed by a relatively bigger circle here. So we can still get the survival probability at the sensor time for this patient A. So this is which is a vertical location for this circle here. And for the rest of the stars, we know they already belongs to the interval that they should be. And for this green star, green circle, how do we decide which interval should they belong? So what we do is we uniformly distributed this star to the subsequent interval that it belongs to. And mathematically speaking, it's a relatively long equation, but the idea is a uniformly distributed between now and 0. So we're ready to make a proposition now. So the proposition is discrimination and calibration are 2 distinct concepts in model evaluation. And specifically, we can have a model A that generates the prediction like this. So what does this prediction tells us? This prediction, we can first draw, extract or calculate the median survival time for this distribution. We can compare the order of the event time, predicted time, and the observed time, and see that they're perfectly aligned. The order of the triangles or diamonds, and the order of stars are perfectly aligned. And as to the calibration, we see that all the stars are located at the first interval between 0 and 25%. That means it is perfectly discriminated and has poor calibration. And on the other hand, we can have a model B that has poor discrimination and perfect calibration. So for the sake of the presentation, I do not go through it one by one. And we also have a model that achieves perfect discrimination and perfect calibration. So that's the idea. We can discrimination and calibration are 2 distinct concepts in model evaluation. So our objective is to improve models' calibration power. And if you look at the literature, there are some few methods try to improve the calibration already. And I call them objective-based method. What they do is they usually involve the penalty term added on top of the regular negative log likelihood loss. However, this multi-objective learning is hard to optimize because first of all, it involves small hyperparameter. It involves a lambda here and involves maybe temperature hyperparameter in the penalty term. And then second, which is more importantly, this multi-objective tends to be dominated by one term. So to illustrate the idea, we perform some experiments, preliminary experiments. Okay, so we gradually increase the lambda in this for this objective-based method. And as we gradually increase the lambda, we observe that the calibration can actually go better. This is what we expect. However, the discrimination power gets dropped. So this is what we call discrimination calibration trade-off. That means for this objective-based method, we cannot have good discrimination and good calibration at the same time. However, if you look at the right side figure, so this figure, this right circle here is the method we propose that can achieve both good calibration and good discrimination. And this red star here is another method called Kaplan-Meier. So Kaplan-Meier is a method that doesn't count the features. So it's a group level prediction. So that means it doesn't have any discrimination power for the patient. So in this case, it has the worst possible discrimination. But however, the next property of it is it guarantees to asymptotically calibrate it so that it has the highest possible calibration power. So the new objective here is not improve models calibration power only, but instead we want to maintain the same discrimination ability at the same time. So for the at the rest of the presentation, I will talk about 2 methods, and each of them has advantages and disadvantages. So we inspired by this motto here. By Mozart, it says the shorter way to do many things is to do only one thing at a time. So we propose a post-processing method. We start with some survival algorithm, some random survival algorithm. You don't need to know exactly the algorithm is. We divided a training set from the data set, and try to fit the survival algorithm and get the fitted model. So in this phase, we're only focusing on building the discrimination power for the model. That means you can do whatever you want in the training phase in your optimization strategy or in your objective function to maximize the discrimination. And in the second step, we're doing a post-processing. That means we extract a second data set, second subset, conformal set, and we're going to calibrate the fitted model using this conformal set. And in this phase, we're focusing only on calibration. And the next property of the proposed two method is that although they increase the calibration, but they do not compromise the discrimination power that we established in the first phase. And another nice property is our method is model agnostic. So you can use either neural network survival algorithm or ensemble-based survival algorithm or tree-based or whatever you want. And you can use stochastic gradient descent or expectation maximization in your training. So the first method is called conformalized survival distribution. And I divide the method into 3 steps. The first step, we discretize the survival curve as some specific percentile levels of it. So as illustrated by this figure here, we discretize the distribution into 3 different quantile levels, 75%, 50%, and 25%. And this 3 quantile level is just for demonstration. In the real world, you can have more quantile levels like 9 ranging from 10, 20 to 90, or like 19 ranging from 5, 10, 15 to 95, or even 99 percentile level for every integer between 0 and 100. So after we discretize the curve, we call the discretized curve the percentile value. So this highlighted dot here means this is the percentile value for patient B at 50 percentile level. So after we get this discretized curve, we're going to calculate the conformity score. So the conformity score is calculated by the percentile value minus the true time. So it means if the conformity score is less than 0, then it means the observation conforms the prediction. And if the conformity score is greater than 0, it means we have an error here. And ideally, if a model is calibrated, then we want alpha percentage subjects having the conformity score less than 0, and 1 minus subjects have conformity score greater than 0. To illustrate this concept, we take a look at the 50% quantile level or percentile level. So because 50% percentile level exactly represents the mean survival time. So for the definition of mean survival time, it means 50% of the subjects should have the mean survival time less than their true time. And the rest 50% of the subjects should have their mean survival time greater than their true time. So that's what it happens if a model is calibrated. And what if a model is not calibrated? We need to adjust the curve. And how we're going to adjust the curve? We're going to subtract a fixed value for every quantile prediction for the curve. So to illustrate it in this curve here, so this is the original discretized curve we got. And we horizontally adjust the curve at each quantile level, percentile level, by the same amount of value. So at 70%, we maybe adjust the percentile value by 0.1. And at 50%, we might horizontally shift it by 0.2. And maybe for 0.25, we don't shift it at all because the prediction is calibrated at this level. So one important note is because we're shifting the horizontal order, so that the horizontal, we're shifting the percentile value in the horizontal way, so that the horizontal order remains the same, so that we can have this theoretical guarantee that applying CSD to the model does not affect the C-index. And we prove it for both mean and median survival time. And in this presentation, we only talk about median because it's easier to understand. If you want to know more about mean survival time, you can check out the paper. Okay, how about the censorship? We haven't talked about censoring in this method at all. So key question is how to calculate the conformity score for censored subjects. So the censored subjects, we do not know this EI, which is the true event time. What should we do? So a naive way to solve this is to simply drop the censored subject. However, as we all know that dropping censored subjects will lead to bias because censored subjects tends to live longer than uncensored subjects. What about some decensoring method, which means we use some estimated event time to replace this true event time and calculate the rest as previous. However, we tried two decensoring methods. One is called margin and the other is called pseudo observation. They're not so good at performance because the estimated decensoring time, the accuracy of the method is highly dependent on accuracy of the estimated event time. And in many times, they're not very accurate. So what we propose to do is we propose to use a method called Kaplan-Meier sampling. So as we said previously, we have a Kaplan-Meier estimation. This is a group level survival distribution that does not take account any feature values. However, the next property of this is it is asymptotically calibrated. And then we can use this distribution as a prior knowledge. What we can do is for a sensor patient, the sensor at here, we know that there's nothing happened before the censoring time. So we're only focusing on the distribution after the censoring time. And then we can update the prior, which is previously the entire Kaplan-Meier distribution to a posterior distribution. And what we do is we normalize this distribution to make it start at 100% at the censoring time. And mathematically speaking, it is expressed in this formula. And what should we do after we get this distribution? We repeat every censored subject by R times and calculate the conformity scores. And for every times, we draw a sample from this posterior distribution. So for example, if R equals to 10, then we can draw 10 samples from this distribution and replace this EIR here. And what about uncensored subjects? So because we repeat every censored subject by R times, and if we do nothing for the uncensored subjects, then the data set will be unbalanced when there will be introducing some distribution shift. So we do the same thing. We repeat it by R time. But however, because we know the exact event time for these uncensored subjects, we in this repeated values, we use the same value for all of them. And a small nuance here, we also divided develop a new data splitting strategy to maintain the good calibration performance. So the old data splitting strategy divided the data 50% to training and 50% to conformal set for calibration. So the advantage of this split is you get enough data for calibration, and the disadvantage is you get less data for training, which makes your model underfit, which concurrently decreases the discrimination. And in the case of you need to split even a calibration validation set for maybe early stopping or hyperparameter tuning, you will lead to even less training set. So what we proposed to do is we want first split the data set into 90% training and 10% validation. This is pretty normal. You can use 80, 20, or whatever you want. So this validation set can be still using for early stopping or hyperparameter tuning. And someone may think we should reuse this validation set for conformal set. However, in this case, we do not have enough data for calibration because we only have 10% of the data in the validation set. And what we propose to do is we plan to combine this training and validation to form this conformal set. And in this case, we got enough data for calibration, and we do not decrease the discrimination power for the model. So we briefly illustrate our experimental setup. We tested our performance on 11 data sets. And due to the time constraint, I'm only gonna present the results for 3 data sets. And we have 4 different metrics, and for this, we're only gonna talk about the first 2 metrics, which is discrimination and calibration metrics. And for the C-index or the discrimination matrix, you can see that the baseline and the CSD, they're basically having the exactly same values. That means our claim about our method doesn't compromising the discrimination power is correct. And for the decalibration performance, we have another comparison here. We add another comparison here, which is the Kaplan-Meier. As we discussed before, the Kaplan-Meier is asymptotically calibrated, means it can serve as the empirical lower bound for the performance. So looking at those figures, we can see that the orange bar plots, they're always close or even sometimes lower than the empirical lower bounds, meaning our method can achieve close to the empirical best performance for calibration. And we also do a summation over 11 dataset and 10 baselines over 5 matrix. We see that most of the time the C-index is tight and we improve the calibration. However, we noticed some problem of this method. So the first method is cause of the inaccurate KM sampling or Kaplan-Meier sampling. So Kaplan-Meier is asymptotically calibrated. However, if we have a data set that have very high censoring data, the KM can be inaccurate. And on the other hand, if the KM ends as a very high probability, the extrapolation of the curve can be problematic. To illustrate the idea, we have the Kaplan-Meier curve for one data set. And when we can plot the histogram for the sensor and event subjects in the data, we see that this data is dominated by the sensor subjects. And how to extrapolate this curve is a question. We don't know anything after the last observed time in the study. So the extrapolation can look something like this. It dramatically decreases after the ending time. Or it can have a long tail that gradually decreases over the time, or it can have some weird shape like this. So how, because KM sampling, we need the extrapolation, and this extrapolation can cause inaccuracy when the data set has a KM ending at a higher probability. And the second problem we're talking about is conditional calibration. So conditional calibration is a concept for related to fairness. Okay, we have a model 1 that has a distribution, and we have the prediction and the true event looking like this. So unlike previously, we divide the total percentile range into 4 intervals. Now we're dividing it to 3 intervals, 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. And because we're having 6 samples here, we hope that in each interval we have 2 stars. And if we check the histogram, we actually have two stars in each interval. However, if we look deeper, if we divided the whole population by maybe female or male, and we can express male using blue and female using orange, we see that although the in total population is calibrated, but among the female subpopulation, the histogram is not uniformly distributed. And among the male population, the histogram is not calibrated. And we have conversely a model 2, which has the distribution looking like this. And in this case, we can have a conditional calibrated case for both male and female. So this male and female is just for illustration. In real world, it could be races like white versus non-white, or like older versus young people, or any. So that's why it is related to fairness. Basically, we want the model to be conditional calibrated, as it is fair for all the subgroup in the population. So to solve these 2 problems, we propose a new method called CSD using individual probability at observed time. So it's a very long name. We will use aberration iPod for individual probability at observed time. So the first step is we're going to use this iPod value as a conformity score. So we actually use this iPod value extensively in the previous discussion. This iPod value is exactly the vertical location of the star. located in the survival distribution. And based on the inverse transform theorem, it should be uniformly distributed between 0 and 1. And ideally, if a model is calibrated, as we talked about earlier, so in each subinterval, it should have 2 stars. And apparently, in this case, we do not have a uniformly distributed stars. The first interval has 3 stars, and the third interval has 1 star. So how should we do this? So we do this operation. This operation involves 3 substeps. First, we identify the empirical percentile of the conformity scores. So in here, this gray line represents the 2/3 percentile for the conformity score, and this line it represents 1/3 percentile for the conformity scores. And you may notice that after we identify those 2 gray lines, each between the new interval, like 0 to the first gray line and the first gray line to the second gray line, there's always 2 stars located between the new interval. And what we can do is we can determine the corresponding time on the predicted curves that matches with those empirical percentile. And then we can do a shifted to make them vertically shifted to where they belong to. So in this case, we shifted the 2/3 empirical percentile to 2/3, and we shifted the 1/3 empirical percentile to 1/3. And after we do this shifting, we finally got the post-processing method or post-processing model, and the resulting curve looks like this. And if we examine the histogram, it will have both conditional calibration and marginal calibration. And what about the sensor subjects? Well, we draw the same idea from the KM sampling. However, this time we have theoretical guarantee, so stay with me. So for sensor subjects, we know that the sensor time must be earlier than the event time, so that the apple value at the sensor time must be greater than the apple value at the event time. And this is because in this example, for example, the survival curve is a monotonically decreasing function, so that if we have the sensor and event time located at here, sensor is ahead of event, then the vertical location of the sensor is greater or equal to the vertical location of the event. So originally, based on the inverse transform theorem, we have the apple value should be uniformly distributed between 0 and 1. And under the conditional independent assumption, we can now update this prior knowledge. We can update it so we can have the apple value uniformly distributed between 0 and the apple value at the sensor time. So to illustrate this idea, we originally have the perfect simple uniform distribution, which has density of 1 over 0 and 1. And then we know that the sensor time we know the sensor time for this sensor subject, and we calculate the apple value for this sensor subjects. And now we know the event time can only happen at the red ranges. Okay, it's not very obvious here. It's a very shadow area of red. Okay, we know that the apple value for event can only happen in this range. So we updated the prior knowledge into a new distribution like this. And same as the previous sampling method, we can do a sampling from this new distribution and sampling the sensor time by R times. And for the uncensored subjects, we just draw R identical values. So thanks for this new method, we now have theoretical guarantee for the calibration. So the first theoretical guarantee is that under the exchangeability and conditional independence assumption, this the post-processing curve by acypod should be asymptotically exhibit marginal decalibration. And the second theorem states that basically similar condition and acypod will exhibit exact conditional decalibration. And one additional condition we have is if the original estimator is a consistent estimator. So we do perform our experiments on this new on some additional data sets. Specifically, we add some data sets that know to have very high censoring rate or have very high KM ending probability. And for sake of this presentation, I'm going only going to talk about these two data sets, which both have very high sensing rate and have very high ending probabilities. And for the matrix, we're adding one more matrix called conditional decalibration, and this is a novel matrix. So for the C index, compare the baseline, the first method and the second method. You see that the second method is a little bit decrease the discrimination power a little bit. And however, if we consider the statistical test, these differences are not significant. And for the margin calibration, you see that for these two very high censoring data set, the CSD method can actually make the original prediction worse. And the SciPlot, which is a green volume plot here, will actually approaches the optimal calibration power. And similar for the conditional calibration, the green, which is the SciPlot method, will always leads to the best performance for this two very high sensing data set. And we also do a summary here. We have compared to the baseline and CSD, the new method, the second method, ties with the most of the time for the discrimination. And for the calibration, it wins most of the time. So empirically or theoretically comparing the two methods, the first method, it has the theoretical guarantee for discrimination, while the second method has theoretical guarantee for calibration. And the second method also have an advantage for the space complexity, which we didn't cover here. And empirically, the second method performs better in high sensing data sets. And the first method performs better in significantly miscalibrated models. So if you want to use these two methods, you might want to choose them based on your application. So we're ready to conclude. Discrimination and calibration are two important and distinct properties in survival analysis. And purpose method, by adding calibration into the objective function, leads to a trade-off between discrimination and calibration. And in this talk, or in these two papers, we use conformal regression as a post-processing method, which effectively disentangles the calibration from the model's optimization, therefore maintaining the perfect original discrimination. And lastly, both methods allows us to achieve KM level calibration, which is the empirical lower bound. And thanks for listening or attending my presentation. If you want to know more about the empirical and theoretical results, feel free to read these two papers. And this is the GitHub repository for these two papers. Thank you.